Okay, I clicked the start broadcast thing, so we'll see if that changes it.
And I'll go ahead and pull up the presentation after this.
Okay.
That's this time.
Okay,
Close the.
All right, should we get right to it?
yep,
All right. Good morning. My name is Drew Jackson, and along with Mark Yamakaitis and Phoenix Price. Oh, about that. We had some problems with our tickets, so you'll see my name says Ben Wormuth. I am not Ben Wormuth. That is our team lead. I am True, but regardless, I'll press forward. And we'll be presenting today on the design, building, and testing of our team's payload, Marco Polo. We built Marco Polo in the form of a 3U CubeSat, designing it to be a low swap-C laser communication demonstration for small sat applications. After deployment from the rocket at apogee, the CubeSat opens up from the closed position pictured there on the left to the open position pictured there on the right. The lower half pictured, named the Precisely Oriented Laser 1, or Polo, houses the laser gimbaling and visual tracking systems that are used to send timing data. This data is received by the upper half pictured, named the Miniaturized Array Receiver Cube 1, or Marco, and processed to determine the offset time in milliseconds between the clocks on both modules. Immediately following deployment, 3 strands of 9-inch aircraft cable holding both Marco and Polo together extend to full separation distance as Polo falls away from Marco. These cables allow Marco and Polo to move relative to each other while descending under parachute. And so to account for this relative movement, the computer vision software implemented on Polo controls the laser gimbal to keep the laser beam focused on the photodiode receiver, Marco. This ensures that enough timing data is transferred from Polo to Marco to allow Marco to perform consistent calculations of the offset time between both clocks on both modules. And as that lengthy explanation implies, the scientific experiment presented multiple complex and interrelated design requirements that as a team we each had to resolve one at a time. And from the beginning, we wanted to limit the design to a 3U CubeSat form factor to match what is commonly seen in the industry, even though this did present a clearly defined limit on spacing for mechanical and electronic subsystems. And also, early on, we knew we wanted to set the limits of the size and power of the laser being implemented to ensure that the beam would not cause permanent damage if momentarily deflected back towards, for example, student experimenters or spectators during active tracking. I now want to turn, however, to the final 2 design requirements listed in this chart, as these accounted for the bulk of our design work throughout the year. And first, I'd like to discuss the team's solution to ensuring reliable data communication with despite consistent movement of Marco relative to Polo. After considering various methods for rotating the laser along 2 independent axes, we settled on a pitch-yaw gimbaling mechanism that works similar to a joystick to control movements of the laser. And the rings of the gimbal were initially designed using aluminum, as you can see in that bottom left image, to impart a high rigidity during rotation. However, once the team realized these allowed for a degree of slip at the connections with the servo gears, 3D printed equivalents were created and implemented into the design, as you can see there in the CAD model up in the top right. And this final design allowed for both a wide range of motion of the laser beam while ensuring that the servos could exercise a high degree of control on the laser movements at all times. And then to control the gimbal movements, we implemented a visual tracking software that ran off of a Raspberry Pi Zero W that received images from an RPi camera mounted to the top of Polo with a direct line of sight to Marco. This tracking software then operated by taking a constant stream of images of the bottom plate of Marco and performing a series of operations on each image frame, which you'll see here in a second, to isolate the portion of the bottom plate of Marco in the frame. We found that by strictly thresholding by color, we could maximize performance and the frame rate of our tracking solution while effectively eliminating noise in the final frame. Specifically, we performed arithmetic operations on the individual blue, red, and green channels of the image. And by doing this, we were able to remove darker regions around the Marco bottom plate. And then once these modified channels were then recombined with capped addition to a grayscale image, we then used Otsu binarization and inversion to transform that grayscale image into a binary image with a minimal amount of noise. And then to remove the remaining noise, we used built-in morphological functions from the OpenCV library in series, and this produced a final image as clean as the one shown there on the far right, even during various levels of image brightness and movement speed of the Marco plate where that image was taken. And then after producing this reliable coded thresholding algorithm, we began correlating the pixel centroid of the plate section that was visible in frame to the servo angle pair, which points the laser at the center of the Marco receiver at that instant in time. And we achieved this by setting both servos to known angles and then manually moving Marco with cabling taut to the position where the laser is shown on the center of the receiver. And then images were taken at each of the 240 angle pairings that we tested. And then we analyzed this data to determine the corresponding pixel centroid of the plate in frame. And then the results of these tests, plotted in the top image, verified that we could indeed reliably derive two functions to calculate the servo angles in terms of the centroid we retrieved on camera. And then when we created the two fitted functions shown in the bottom image and hard-coded them to the joint tracking algorithm in charge of both threshold and images and oriented the servos in real time, we found the tracking formed to a high degree of success. And then finally, we added a extra predictive tracking. Oh, sorry, one more part on that. And then finally, we added a predictive tracking element to the software in the form of a third-order Taylor series. And we found that this was able to successfully reduce the lag that we saw in servo movements behind the movement of the receiver by about over 50%. In the next slide. And then both the relative motion requirement and low swap laser requirement had major impacts on the design of our team's photodiode receiver. In particular, we needed a receiver large enough to allow for reliable communication of data despite lag between movements of the Marco receiver following by the laser gimbal. Also, to produce a high enough carrier to noise power ratio to reliably reconstruct the data sent over laser, we needed photodiodes that had heightened sensitivity to the red light spectrum. And so to achieve both of these specific requirements while also minimizing the price of our solution, we decided to produce our own photodiode array PCB and then reflow solder individual photodiodes with heightened sensitivity onto that board. And then the resulting board then outputted spikes from the laser as analog readings, which then needed to be converted back into a simple digital signal to be received on our TNC microcontroller. And then this was achieved by designing a custom Schmidt trigger and carefully selecting resistors to create a cleaning digital output after just a single filtering stage. Next slide. And then once the tracking, gimbling, and other electronic systems were in their final flight-ready configuration, we conducted a final ground test, which yielded key data on transmission performance in terms of the lateral acceleration experienced by Marco. In the top graph here, you can see 3 percentages listed, which are calculated over 4-second intervals. The first of these, shown in blue, represents the amount of information intercepted by the Marco receiver relative to the amount of information received when Marco and Polo are stationary relative to each other. The second percentage, shown in orange, represents the amount of information received that is correctly reconstructed on the UART communication channel. This percentage decreases, for example, with an increased number of misreads, which result when the laser moves off the photodiode board or onto a dead spot between photodiodes during transmission of a character. The third percentage, shown there in green, is a product of the previous 2 percentages and represents the amount of accurate, usable information retrieved by Marco relative to what is expected under stationary, or in our case, ideal conditions. From this ground test, we were able to determine that during periods of relatively constant acceleration, shown there on the left side of the graph, and again, a little bit on the right, the amount of usable information received by Marco was about 40% of the ideal amount. And then conversely, during the period of high jerk there shown towards the end, the amount of total information received relative to ideal conditions was about 45%. And the amount of that information that was correctly reconstructed was also about 45%, for a total transmission percentage of about 20%. Next slide. And by the time of this test, we had already chosen to implement a method for reconstructing the offset time between Marco and Polo clocks by receiving only pairs of correctly read characters at a time. This was done to ensure that when the payload was experiencing moderate to high shaking during descent, that a timestamp could still be reconstructed without needing to read back a single full timestamp correctly. The method for accomplishing this was to send the value of each digit of the timestamp from Polo one at a time, coupled with the letter marking the digits place that represented. And when stitching these digits back together on Marco, however, we found that slight variations in the time synchronization occurred due to slight variations in the time when the data was sent from Polo and the time it was received by Marco. However, of the 332 offset times we received during that ground test mentioned earlier, 85% of these remained within 1 standard deviation of the estimated offset time of 5.85 seconds. And we believe that this confirms that by performing simple statistical analysis on a small sample of offset times, we could tell Marco how to effectively calculate the true offset time between between both modules with a high degree of accuracy. Next slide. And then with this data confirming that our laser communication system functions well under pseudo-flight conditions, we look to confirm the efficacy then of our tracking algorithm in the full rocket test we conducted in mid-April of this year. Back in January, another test launch confirmed that our inactive deployment method for the payload would successfully eject the payload at apogee, and that the small main parachute we attached to the payload would catch air shortly after the start of descent. This was in spite of the fact that a commercial motor defect in this test almost burned the payload up, if not for the decision a week prior to use a dummy payload made of aluminum stock into place. And while we were anxious to put our payload in harm's way then, we assumed rather reasonably that by April, lightning would not strike twice. And as you'll see, however, in this data, this particular test left much to be desired. Data from the payload pressure sensor shown in the top figure appears to confirm a hole in the body tubing section housing the payload, which resulted in a non-ideal rocket tubing separation event at apogee. And the black powder charge separation occurring at that time, if it were successful, would have deployed the rocket drogue and with it pushed the payload out into the air to begin descent under parachute. But because this did not happen, the rocket instead came back down, crashing into the field where the flight test was conducted without a deployed parachute to slow it down significantly. And while this hard landing ejected the SD card on Marco, erasing much of our data and tilt data from the payload after apogee, key results were still obtained from this test. Outside of partially shattered 3D prints and bent black oxide screws, we pulled the payload out and we found that basically it remained fully intact despite having remained inside the rocket and crashed along with the rocket body. And so in summary, no electronics had shorted after that test, nor had any major mechanical components broken on landing. And so basically our payload made it through what we consider to be the worst possible shock it could experience, and yet remained in healthy enough condition that after analyzing it, we determined that we could rebuild it with just a few hours of work. And next slide. And with all these experiences in mind, we believe as a team that Marco Polo proved an effective laser communication demonstration that implemented visual tracking software to maintain a reliable line of communication between two independently operating modules. Future work could expand to the research of this project along multiple fronts. For example, we could produce an updated photodiode board that allows simultaneous red, green, and blue wavelength transmission and data reconstruction using multiple Schmidt trigger circuits. This in particular, for example, could have applications in channel switching and in data encryption for military purposes. Our experience designing the Schmidt trigger also demonstrated the ability to make active filtering circuitry. Specifically, servos and potentiometers, which were used to design that Schmidt trigger, could be implemented into a final filtering design and be used to automatically adjust the cutoff voltages of that Schmidt trigger based on the data that's incoming. And this could potentially allow for different wavelengths of light to be read correctly back by the same photodiode receiver. So although photodiodes have a certain sensitivity, we could effectively change how the signal was filtered to bring it back to a digital signal that can be correctly read on a microcontroller. And now with that, I just want to say thank you so much for giving us the chance to present today. And now I'll go ahead and open the floor to questions.
What's the diameter of the emitted laser beam when it gets to the 10 inches away?
The diameter, from what I can remember, is about the size of a single photodiode. So I think that would be on the order of half a centimeter, but I would have to check on that.
Okay, and it doesn't matter which photodiode it hits, right? As long as it hits any of the ones on your array, you catch it and okay.
Yes, yeah, we designed it so that all the photodiodes are basically arranged in parallel. So a spike on one is a spike on the output, or creates a spike on the output.
And what color was that laser you used?
Oh, I did not mention that. Thank you. The color we used is actually a red light as well, so 650 nanometers to be exact.
And what was the area percent fill of your array, your receiving array? How much gutter space did you have?
Ooh, that is a really good question. I'd say we covered most of the central area. I'd say maybe about 10-15% of it had space that could be defined as dead space.
Okay.
Were you able to track how much your gimbal had to be exercised or how much work it was doing? And could it keep up?
We did perform a few different ground tests after we had the tracking implemented, but before we did that final ground test, and those confirmed that we estimated that maybe for about 80% of descent after basically it came out and it was shaking around for maybe about a minute or so, it would be able to keep up just fine. It was just during that first period of high jolting and movement that it might have some issues.
What's the frame rate of your image capture?
I'll actually go ahead and let Mark Yamakaitis answer that because he did a lot of the work with optimizing that code. Mark?
After we process, after we do all of the processing, our total frame throughput is about 15 frames per second total. And that includes all of the processing, including the filtering and retrieval of the frame.
And how does that compare then to your servo lag?
I guess that's another good question for Mark.
The servo lag, I don't know if we measured specifically the lag between sending the signal to the servo and the time it takes for the servo to react, unless I'm mistaken, Drew.
Yeah, I don't think we measured the physical time between the lags there, but we did measure. I know you did some analysis with determining how, I guess, the predicted position changed when you updated the tracking algorithm. Is that correct?
Yeah, we include we use the previous, we take into account the delay in processing time by looking at the velocity and acceleration of the payload by using like a backwards like finite difference method to measure velocity, acceleration, and jerk. And that is able to help us predict where the payload will be by the time we've finished the processing. And that reduces the error by about 50% between.
Cool. So what do you predict your closed loop bandwidth to be then of that whole control system?
I didn't get what you said at the end.
So what do you expect the closed loop bandwidth to be of the full controlled system?
I think I have to speak for all of us and say that we don't have much experience with determining that, but I guess I'd be more than willing to look it up and try to determine an estimate for that,
Okay.
if we could.
Did I understand correctly that the reason you went from aluminum supports on the gimbal to 3D printed was to reduce mass to have higher control authority from the servos?
Yes, that's right. So what we had happen is we did the correlation testing and we got some weird relationships when we ran it the first time. And what we realized was if you tried to force the laser to move, the actual clips would actually slip on the servo rings. And so what we were able to do is instead of trying to remachine basically a metal clip where we had a really hard time trying to get the actual servo gear teeth drilled into that, we were able to just use a 3D print and get a pretty tight fit from that instead. And then that prevented basically any slip of the ring while it was rotating.
So in regards to your UART communication stream between the two devices, what baud rate were you using?
We were using 2400 baud.
Okay, and did you have any kind of error correction algorithm encoded into that bit stream?
We actually did not. We were able to get the Schmidt trigger so that, to our best understanding, it effectively varied the lengths of the peaks and troughs in our data signal, and that was able to effectively reconstruct the UART signal so it could be fed right into an RX pin and be read back at 100% success when we had no relative movement between the laser and receiver.
I like how you addressed each digit though as well, so that if you lost sync, you knew where you were when you picked back up. That's clever.
Oh, thank you.
Anything else?
I'm just, so okay, so now your presentation's kind of concluding. What surprised you in developing your payload? What was the biggest challenge that you didn't foresee?
I think, oh, that's a really good question. I'd say what surprised me the most is just the amount of learning that went into building all the individual subsystems on the payload. Because throughout the year, I've got to be honest, I was in Kansas, Phoenix here was back in Virginia, kind of near George Washington. Mark was in New Jersey, and we basically worked together with me having most of the stuff at my home to put this thing together and do the best we could to basically assemble it in-house, virtual. And just the amount of learning that I did, just trying to basically solder all the PCBs together, working with Phoenix to design the PCBs, and working with Mark to get the code implemented onto the RPi and kind of get that set up. It was just a really fascinating experience. And I'd say one of my biggest disappointments is that I couldn't share that with everyone else on campus, because it really is an experience. And I think that it's definitely something that I will carry with me for the rest of my life. It's just the learning curve for that, and just the amount of work that goes into it is just spectacular.
Well, that's an ambitious payload. You not only had the electronics data transfer you had to deal with, but then you had a gimbal, the laser, and everything. So, yeah, you got a lot going on.
Do you foresee an option of flying this again sometime?
That's actually a very good question. Our faculty advisor was actually asking us the same thing about a month ago. I think because of how it worked, where I was kind of doing the majority of the work in-house, I would probably definitely want to fly the payload again when we get back on campus in the fall, but also continue research into the laser communication and applications of it. It's probably a senior design project, because I'll be a rising senior this year. And so I guess exploring both avenues of, yes, launching it and testing it for real this time, and then also exploring and further researching into it. Definitely.
You know, even if you could go throw it off a cliff or something somewhere, it would be really cool to see how that performs.
Yeah, I'm really looking forward to the chance. Phoenix and I basically brought out entire EC laboratories with us to our dorm where we're staying for the summer. And so we have probably the resources to maybe try and rebuild it, and maybe try to do it again this summer. We just would need a couple of things from our university, but we could probably get those shipped to us actually, and hopefully do it this summer. I mean, that'd be amazing.
So do I understand correctly that the two halves of the payload, when they're in the rocket, there's nothing that holds them together, just compression, and then when it separates, then they just separate because one of them's attached to the chute. Is that correct?
That's a good question. Phoenix, can you go back to the CAD model? So we actually have, because the twisting of the aircraft cable was really hard to kind of keep that together without rotating apart. So basically, to add an added factor of stability, there's a couple of bolts you can see right there, where basically we cut a couple of holes in the top plate of Polo and the bottom of Marco, and then placed a long bolts through there and screwed on a couple of nuts to that. And so after we rotated about like 180 or 540 degrees, we can actually set Marco on top of Polo, and so that is fixed while it's in the rocket. And then what we tested is we were able to verify that releasing that or it coming out of the rocket would not, those bolts would not catch, and it would be able to still separate, and then it would start to unrotate.
Oh, they're just pins?
Okay.
Keep it from twisting itself?
Mhm.
Okay, I see.
But they do fully separate to where there's no mechanical engagement other than just the tether.
Correct. Yes.
Okay. Probably a strain factor in the cable for pushing the apart.
Yeah, it's just standard aircraft cabling there. Very, very rigid.
Since then is 9 inches.
Well, let's see. The cables themselves, I think, are 9 inches, but now that I'm thinking again, the eye bolts extend that a little bit, so it's more along the line of 10 inches.
Okay.
And then the gimbal, I'd say, is about the center of the gimbal is about 2 inches further out from that, and then the receiver is like maybe another ½ inch up from the bottom plate.
So you have an optical path length of about a foot.
Exactly. Yep.
And all the data is stored on board, correct? There's no real-time telemetry?
There is a real-time telemetry system in the form of a couple of XP modules. We've used those in the past and have had limited success with them, but while we were testing, we were able to get that system to work on the ground. Obviously, whether it worked in the air, we weren't able to confirm that, unfortunately, but We used that to transmit some of the laser transmission data on the ground in real time. And then we also used a couple of PCBs that housed teensy microcontrollers and SD readers. We were able to effectively save all of our data onto those two SD cards during flight.
So
One on Marco and one on Polo.
is there a GPS? What I'm getting at is it separates from the rocket. The rocket has a GPS, you know where you can find it. But if the payload went somewhere else,
Oh, yes.
if you can't, how do you find the payload if it goes somewhere else and retrieve your data?
Yes, that is a very good point as well. Let's see if you can look at that slide again real quick. There is right up there up top, if you can zoom in, might be a little hard to see if you circle right around there. So there's actually a couple of COTS telemetry systems up there. The one in green there is a featherweight altimeter, and we were able to get that to work while we were testing it during January. And then right there on the left, you see that brick, that 3D printed brick, that houses an Iridium OEM, a GSAT micro OEM module. And those would have basically served to help us locate the module if it had come out of the rocket. During that April flight test, we were using just the featherweight altimeter because of some issues with the Iridium, but it was designed essentially to have both in there and both actively function, excuse me, at the same time.
Okay, thanks. All right,
Thank
we better cut it off so we have time to get ready for the next one, but unless there's some final comments or questions. Nice job, guys.
Yeah, well done, guys. Super cool. Thank you.
Well, thank you very much for having us.
Thank you, guys.